Now we are going to hear the keynote talk by Carmit. Carmit had her PhD from Bar-Ilan University, where she's now also a professor. Carmit has done a lot of interesting and varying work, both in the practical and theory aspects of cryptography. And today we'll be hearing about the work that actually merges these two elements very, very nicely. She has done work on theoretical work covering lower bounds, on interaction of multi-party computation, fairness in multi-party computation, then more applied work in particular functionalities such as set intersection, pattern matching, interesting works with always some nice tricks and twists. She also is the author of a book called Efficient Secure Two-Party Protocols, Techniques and Constructions with Hugo Lindell. There was a time in the history of the world where people would have shelves with books. I would definitely have that book in their shelves, even though it's also very old, 10-year-old, I think, book. Actually, and many things happened since then. I think it still covers many of the basics that people should know.
Yeah, the movie is better, by the way. The movie is better. The movie.
I don't know the movie, so there's something to look forward to. So anyway, let me welcome Carmit. And now she's going to talk about Diogenes, lightweight scalable RSA modulus generation with a dishonest majority. Carmit, your
Thank you very much. Okay, now I can share my screen. Great, do you see my slides?
Mm-hmm.
We see the presenter view though.
The presenter view?
Yeah, you may want to switch the screen to the one that is.
Yeah, I don't know why. Let me do that.
Mm-hmm.
Okay. Okay, let's do it like that. Okay. Is that good now?
Yeah.
Good. Okay, so thank you, Hugo, for the kind introduction, and thank you for the organizer for inviting me to give this talk. This work is made possible due to a group of very talented people. On the research/academic side, we have Megan, Yuval, Daniele, Abi, and Mutu. And on the engineering part, we have Yuri, Tariq, and Ruhan. And this project is about pushing the boundaries of practical MPC. Okay, so let's start by giving you some context. So an RSA modulus is a product of two large primes of the same length, and we call such a product a biprime. And throughout the history of crypto, such moduli had quite many usages, starting with the well-known RSA encryption scheme. And most recently, they've used as an implementation for verifiable delayed functions, or VDFs. VDFs have gained a lot of popularity recently as a strategy for generating randomness on blockchain networks. And basically, this object is a core object in the Ethereum 2.0 project that is sort of going to shift from proof of work to proof of stake. And VDFs will be used as a source of randomness and will contribute to the scalability of the system for how to establish the next iteration. Here's an example of a time lock puzzle. It's a function due to Rivest, Shamir, and Wagner that is computed using T steps by repeated squaring and modulo an RSA composite. And the point of computing this function is that it cannot be computed faster, let's say using hardware. And only if someone holds the prime factors of n, then it's possible to verify the outcome of the function in less than t steps. So this is what we call designated verifying. You need to know a trapdoor in order to verify the output of the function. And pretty recently, by two very nice papers by Krawczyk and Wasilewski, they showed how to make this the verification process of this function public by adding a non-interactive zero-knowledge proof for discrete log, while pushing most of the work to the prover side. So for that, it is required to generate n with an untrusted setup so that no one knows the prime factors of n. And this is the goal, this is basically the goal of this project. So this is where we come into the picture. And the goal of this project is to build and design a distributed protocol to sample n such that no party can learn the prime factors. This is as instead of just having a trusted authority or entity generating by himself. And note that the more parties we have participating in the protocol, the less trust we need to put on an individual party. And more specifically, the parties or each party will randomly generate or sample shares, both for P and Q. And those shares will be combined to create the RSA modulus. So one of the main goals of this project is achieving scalability, where we want up to 1,024 parties to participate in the computation. And additionally, we want a dishonest majority. We want the security to be, the protocol to be secure in the presence of corrupting even n-1, up to n-1 parties actively. Meaning we could do with having a single honest party in the system. And this stands in contrast to protocols with many parties that require honest majority. And note that the advantage of working in a dishonest majority setting is that a party does not need to trust anyone by itself. And I want to stress that such a protocol, designing and implementing such a protocol hasn't been done at this scale before. So just a few words on MPC, secure multi-party computation. So this is a tool that allows to eliminate a trusted party, right? Instead, the parties can communicate directly while obtaining the same security as in a trusted party setting. And security is modeled in the presence of an adversary that corrupts a subset of the parties. And we basically follow two types of such types of attacks. A passive adversary is a benign adversary that assumed to be following the protocol's instructions, but trying to violate the privacy of the honest party. While an active adversary can follow an arbitrary attack model and can violate basically anything in the protocol. Definitely correctness, for instance. So it's a much more, it's strongest and a realistic attack model. Another aspect of defining security is regarding the number of corrupted parties. In the honest majority setting, we assume that strictly less than half of the parties may be corrupted, while in the dishonest majority setting, all parties but one may be corrupted. And the combination of having active security in the dishonest majority setting is pretty much one of the most challenging settings to work in. So by now we already know that MPC is very useful and have many important applications. And the purpose of this talk is exactly one of these applications. Okay, so the problem of distributively generating an RSA modulus was introduced by the seminal work of Bunnell and Franklin in '97. And so this basically introduced the problem and also gave the first solution. And their framework remains the basis for most of follow-up works till today. And there has been a long sequence of works following the Bunnell-Franklin paper. And let me highlight a couple of relevant papers in our desired setting, right? End parties and dishonest majority. So there were two previous papers in this setting. One, which is a joint work with Mickelson, Rabin, Toft, and Nicolsi, where we used dedicated zero-knowledge proofs to ensure correctness. And the other, a very recent paper by Chen et al., which employs pairwise OT communication channels. And let me just say that both of these works are not efficiently scalable to the scale we want, 1,000 parties. Also, I want to, since we are talking about implementation, let me focus on the two implementations for this problem. There's the paper I mentioned before, and the more recent one, denoted by FLOP. However, both of these implementations chose to focus or benchmark the passive variant of their protocol. So FLOP only implemented a two-party variant with passive security. And this paper made a significant improvement over prior work solving this problem. And their implementation was, up until that point, the state of the art. We at Ligero were challenged by the Ethereum Foundation to come up with a protocol and an implementation that meet the following goals. So generating the same length of an RSA modulus. Our protocol requires to achieve active security with identifiable abort. In this setting, if the protocol fails to complete, then it must identify at least one cheating party. And this property is pretty hard or challenging to achieve because it requires from the parties to reach into a consensus about the identity of the cheating party. In addition, as I was saying before, we need the protocol to run with 1024 parties. The spec of the parties, they need to be, we want to support lightweight participants that only use 2 GB of RAM and a single core of CPU. They also need to run very low bandwidth of 1 megabit per second, and where the latency is 100 milliseconds. The overall communication per party must be bounded by 100 megabytes. And finally, the running time of the protocol must be bounded below 20 minutes. So this was our challenge, and this is what we did to achieve it. So let me give you a roadmap of the steps we took in this project. Okay, so a common paradigm in MPC is to start with the design of a passive protocol and then compile it into the active setting. And we have different methods to run this compilation. So our first goal was to identify the best scalable passive protocol. So let's go back to the Bunnell-Franklin framework. So they gave a very nice framework for a distributed RSA modulus generation based on 3 steps that we follow here as well. And here's a quick overview of how it works. So in the first step, the parties choose their prime shares for P and Q. And I want to stress that these values are randomly sampled. So there is no guarantee that they end up to be primes. And now, since the next steps are quite expensive, we want to sort of disqualify some of the candidates that we already know are not primes. And this procedure is called a trial division. In the next step, the parties run a secure multiplication protocol to get a candidate for an RSA modulus N. Now at this stage, we will have no, still we have no idea whether the sum of PIs and QIs are prime, right? We sort of filtered some of the candidates in the previous step, but it's not enough. It may still not be primes. So therefore we need a third step where the parties test whether the product is a biprime. And let me just remind you that the prime factors are a secret. So we can't just test assuming we know those primes. We need to test on the public product. And here we use a biprimality test originated also in the seminal work by Bunnell and Franklin. So let me now explore in more details these steps. Okay, so let's first start by examining the candidate sampling and trial division step. Okay, so naively, when you choose a random string, the probability that it will hit a prime is related to the density of primes, right? And it's approximately 1/1024. But note that it's easy to make sure that the parties sample an odd number. So by doing so, we can reduce this probability into 1/500. But still, to hit a biprime, right, we need 2 primes. We need, in expectation, 250K samples. And that's a lot. So we would like to use a more sophisticated way to sample those shares. So instead, we will do filtering. We will filter the candidates. Basically, we will check whether the candidates primes are divided, but by, let's say, the first 150 small primes. And then disqualify all those primes that are divisible by at least one of these primes. So doing that will enable to reduce the probability of hitting a prime into 1/60. So overall, we will need 3,600 samples in expectation, which is much better than what we had before. Okay, so there has been several techniques for sieving the candidates in the literature. So previous papers followed an approach where the parties first generate P and Q, of course, obliviously, and then running this sieving phase. And if both of these tests passed, then they multiplied to generate the product. In the papers I mentioned before, so in this previous paper, we used El-Gamal and dedicated zero knowledge proofs to run this test. And in the FLOP paper, they used 1/k oblivious transfer, OT, which is a fundamental building block in secure computation. And let me just note that both of these techniques are not scalable with the number of parties, especially because they require pairwise communication channels. Also, maybe it's a good place to point out, so indeed OT is considered practical in MPC due to techniques like OT extension. But another point regarding the FLOP protocol is that the domain of the sender grows with the domain of the input of the sender grows with the domain of the prime we want to test. So basically, you need to reduce 1/k OT into 1/2 OT if you want to use all these very fast techniques. And that requires some extra overhead, definitely in the active setting. Instead, in our project, we use an idea recently introduced by Chan et al., where we take the dual approach, meaning we first sieve the shares, and only later we construct the prime shares. What do I mean by that is that we basically sample the shares over a small prime domains. And then we validate those shares over the smaller domains. And only if they pass the verification, if they're validated, then we use the CRT reconstruction algorithm to reconstruct the shares of P and Q. And this approach is much more efficient than previous approaches and allow scalability. Okay, so that was the first step. Now, switching to the next step, this is about a fundamental building block in secure computation. So pretty much any generic protocol can be abstracted using this functionality. And we have many protocols for computing this functionality. And it is the biggest bottleneck in MPC protocols. So that's why it was important to identify the best protocol for this task. So we reduced this task to a secure multiplication. And let me explain this in the with only two parties. Here we have, the parties have shares to the functionality. So they have shares of two values, A and B. Let's say these are additive shares. And the functionality basically reconstruct A and B, multiply the two values, and creates two additive shares of the product. So this is basically what a secure multiplication achieves. And in the two-party setting, we have good protocols to compute, to realize this functionality. I mentioned oblivious transfer before, and if you are familiar with oblivious linear evaluation. But these protocols are not scalable as the number of parties grow. And we definitely need a different approach. So the approach we're taking here is based on threshold additively homomorphic encryption. And it's an encryption scheme. So it's a primitive that is defined based on 3 algorithms, where the key generation algorithm and the decryption algorithm are basically protocols. So to generate a public key, each party chooses a random share of the secret key, and there is a protocol that running and creating out of these shares the public key. And since no party knows the secret key in the system, then if you want to decrypt, then we need to run a protocol for decryption. Each party contributes to the decryption using its own share. Okay, so in addition to having a threshold primitive, we also require that this encryption scheme will be additively homomorphic, meaning that the encryption scheme supports 2 operations of addition and scalar multiplication over the ciphertext. We further use an untrusted coordinator to aggregate and broadcast the messages received from all parties. So this coordinator is useful for having the parties run with a small memory and low bandwidth, since they basically outsource their computations on the public data to the coordinator. And it's useful because the coordinator doesn't require using any private randomness. It doesn't have any input to the computation. Basically, it takes only messages sent by the parties and aggregate them. And I'm stressing, this coordinator is untrusted. So it will eventually publish the transcript, the whole transcript of communication on some bulletin board to be verified by anyone else that the computation, the operations were performed correctly. And I just want to emphasize, we don't really need an extra party introduced in the protocol. I mean, any of the parties can fill in the role of the coordinator. We use the coordinator as a means to achieve lightweight computation for the rest of the parties, where the coordinator will be much more powerful machine. Okay, so this is how our protocol works. So we have 2 columns. This is the column that you can think of what the parties are computing, and this is for the coordinator. So in the first phase, there's just some setup phase, where the parties choose their secret key shares and produce a public key. And in the second phase, the parties generate or sample their shares for P and Q, and they encrypt this, the PI share and send it basically to the coordinator, which aggregates the ciphertext and send it back to the parties, broadcast the ciphertext. Next, the parties multiply by a scalar, by the QI share, the ciphertext they received in the previous step, and send it back, send it to the coordinator, which aggregates those ciphertexts and send it back. And now basically we have the encryption of P and Q, which is decrypted using a protocol as I explained before. And I just want to say that this is not a new protocol. I mean, it was known from the literature before, right? So Franklin and Haber designed this as a semi-honest protocol based on threshold AHE. And Kramer, Domrad, and Nielsen extended their protocol to the active setting in the honest majority setting using dedicated, special-made, custom-made zero-knowledge proofs based on a number of theoretic assumptions. But their protocol can be easily extended to the dishonest majority setting as well. Nevertheless, it's impractical. Okay, so the next question is how to instantiate the threshold AHE in this construction. Okay, so the first natural choice would be to use Pallier, but that's a circular choice because the public key of Pallier also requires an RSA modulus. So that doesn't work. The second choice is using El-Gamal, but El-Gamal doesn't support efficient decryption because it requires computing a discrete log. So what about LWE? The problem with LWE is it doesn't support all HE operations efficiently. Specifically, it doesn't support scalar multiplication the way we want it to support. So we are left with ring LWE, which turned out to be most suitable for this project. It supports both operations, it has better parameters, and most importantly, it supports packing. So packing is a feature where you pack many plain text into a single ciphertext. So that feature has a very important role in scaling or making our protocol scalable. So just in the third step, I'll just say quickly, we basically have the biprimality testing, and we use the original test from the Bunnell-Franklin paper. And just recalling, remember, we cannot test directly on P and Q, so we test the product. And for people familiar with primality testing, this is an extension of the Miller-Rabin test. Good. So the next step, I'm going to show you how to get active security. So the GMW paradigm is a beautiful result that showed the first application for zero knowledge, much before we had Bitcoin and blockchain. And it is one of the most fundamental results in MPC and the first compiler from passive to active. Unfortunately, it has been always dismissed for not being practical due to using generic zero knowledge proofs. And I'm going to show today that employing zero knowledge proof generically can make this paradigm a reality. So far I talked about MPC, which seems indirectly related to zero knowledge proofs. And in the rest of the talk, I'll talk about how to use or how to employ zero knowledge proofs. Okay, so let me explain a little bit about the GMW paradigm. So here's this is a picture of a passive protocol, right? Remember, the parties have their secret inputs, secret randomness, and they exchange messages. In the GMW paradigm, the parties commit to their input and randomness ahead of time, and then attach to each message a zero knowledge proof that proves that this message was computed correctly based on all previous transcripts, as well as the committed input and randomness. Our modification to this paradigm is based on the observation that the RSA functionality doesn't have any secret inputs. So instead of giving a zero knowledge proof per step, we can basically push all the proofs towards the end, to the last step. And if a party is cheating and get caught, then no privacy violation has been caused because there aren't any secret inputs, any secret randomness. And this is great for having lightweight messages sent in the first step, almost as in having a passive protocol, and then push all the verification phase or validation procedure towards the end. Again, I'm stressing this paradigm doesn't work in general because a party can cheat somewhere in the middle and violate the privacy of an honest party. So by the time we'll get to the zero knowledge phase and try to catch it, you already stole all the secrets of the honest party. Okay, so and the next question was about how to, what kind of zero knowledge we choose for this project. And we had several criteria of how to, of what should the zero knowledge be associated with. And the most important one is that we were looking for a proof system that can run with, since the parties were limited in computation, right, or light participant. We wanted to support light participant. The prover must be light as well, the prover's algorithm, because the parties are going to run the prover's algorithm. In addition to that, the proof generation must be memory efficient because of the memory constraints of the parties. As I discussed in the previous slide, it must support the feature of commit and proof. And finally, it must be flexible enough to be able to work over different rings or fields that emerge in our protocol. So based on all this, we chose the Ligero proof system, which introduces a communication complexity that is proportional to square root of the circuit size, used for verification, and supported the other features I mentioned before as a lightweight prover's algorithm and memory efficient. And it's very friendly with the commit and proof feature. More specifically, we combined the Ligero proof system with a Sigma protocol for running this Jacobi test, this test I mentioned in the third step. So in that step, we basically prove or use the Sigma protocol to prove a discrete log in groups of unknown order. This proof is an extension of the classic SHUP protocol for discrete log. And in order to combine the two types of proofs, we basically showed that the third message in the Sigma protocol, which is linear function of the prover state and the verifier's challenge, is consistent with the other witness of Ligero. So that was how to combine the two proofs, and such a combination have been studied I mean, how to combine algebraic and non-algebraic type of proofs have been discussed in different contexts, also by the blockchain community. Okay, and we used Ligero for proving our lattice-based operations, and also how to sample the shares over the small prime field. Okay, now I want to stress that so this ring that we were using for lattices is basically computed based on as the product of 21 different primes. Okay, so in order to work over this ring, it is enough to work over the primes factors of the small primes, which what we did here. And as a result, we had 21 different proofs, one for each prime. So this summarizes the details of our protocol. So you see that all these steps are related to the passive protocol. And here at the end, we had the phase that combined Ligero and the Sigma protocol, where at the beginning, we had a phase where the parties committed to their randomness used throughout the protocol and in the proof. Now, here are some running times of our passive protocol first. And there are several important points of, from this table. So first, we were able to run our experiments up to 10,000 parties, which is the first time that an MPC experiment ran at this scale. For the 1,000 parties, we were able to do it, to run our protocol in 3.5 minutes. I just want to point out that the parties ran on a T2 small configuration on AWS. And the bottleneck was the coordinator. So basically, we could have hoped to have much slower increase in the running time, but basically increasing the number of threads that the coordinator could use. So I mean, could use the number of threads as the number of parties. But we were limited to using only 128 threads as, by the Amazon machine. So that's why the coordinator was the bottleneck in this, and you can see the increase in the running time. As for the active setting, so here we had so let me first so this is the breakdown of the three main phases in the protocol. So that was a slightly different experiment. It was configured differently with respect to the regions. So that's why the running time of the passive protocol was lower. And you can see that the overall running time is less than the sum of these three numbers. And that's because since we had 21 proof, we can interleave the process of proving and verifying. So we don't need to wait till all the proofs to be generated at the end, but we can start verifying in parallel to generating the proofs, and that saves time. And the overall time of the entire protocol is roughly 3 times what we had in the passive protocol. And another point is that the communication is relatively small additive overhead over the passive communication. So the passive protocol required 150 megabyte, and the proof an additional 50 megabyte. And previous passive to active implementations did not have this, did not achieve such a small overhead. Usually, the going from passive to active is a multiplicative overhead. Okay, so let me just conclude by saying that we achieved our goal and met the challenge set by the Ethereum Foundation, except for the communication complexity per party, where instead of having 100 megabyte, we had it was 200. And I mean, it would be great to see whether this code could be run from, for instance, from a browser. And also, let me say that we have done MPC for 10,000 parties, which is roughly the maximum number of parties of active nodes run on Bitcoin. So could basically say that you can use this MPC to run over this network. So the code is available online. We welcome all of you to play with it. And thank you.
Thank you, Carmit. We all you can hear it from all over the world, and you did fantastically with the time. So now we are open for questions. Mutu has been answering quite a few of them. So there are not too many in the chat, so if someone wants to start with questions.
I guess I had a
yes.
question.
Yes, go ahead.
So what are the number of lattice operations that you're doing? Because I understand you're using the ring LWE, using the sort of Chinese remainder theorem optimization model, and so how many lattice operations do you have to do? And in respect of proving inside in zero knowledge, wouldn't other schemes maybe be faster? I understand that's sort of the bottleneck of or the major computation inside of zero knowledge, right?
So, right, so we had a packing dimension of 2 to the 16, right? And the size of the ciphertext is 21 times 62 bits for I mean, that was the number of bits we used per prime, okay? And so all those lattice operations were used for secure multiplication. Does this answer your question?
Yeah, I guess I'll look at the paper for concrete numbers, but I'm wondering whether there is...
Yeah, all the parameters are in the paper, the concrete parameters.
You're very quiet, Daniel.
Sorry, now can you hear me better?
A little, maybe.
Okay. Just really wondering whether there is tests on other schemes, whether other schemes were tested to see if they were more efficient.
You mean other zero knowledge schemes, not encryption schemes, right?
Yes, zero knowledge schemes.
So we had some tests, and basically we ran into memory issues. The main bottleneck was memory. So we did a little bit of testing at the beginning, and we ended up, I mean, understanding that I mean, Vigara will be a best fit for it.
Thanks.
Any other questions? Let me ask a question.
Yeah.
Okay.
So do I understand correctly that you're using the Euler-Jacobi primality test?
Yeah, the test, yeah.
Is that just because of its simplicity, or did you consider other tests?
I'm not sure I'm aware of any other tests. I mean, on the public products. All the
right, okay.
Have used the same test. And I mean, the soundness of this test is half. In practice, it seems to be much smaller. It's a good open problem to improve the soundness analysis of this test.
Okay, so you're using that just because it only requires a modular exponentiation, and you know how to do that in the...
yes, I mean, otherwise, if you want to test directly on the primes, you need to do it somehow obliviously. I mean, either inside the circuit or it will be much less efficient.
I was also curious about the technique you use for is it optimizing the trial division? So if for example, you're trying to generate a prime just without zero knowledge, then we'd probably sample it using a factor wheel. So pick some products of small primes and make sure that what you're sampling is relatively prime.
Right, so you sample the shares over smaller modulus.
Mm-hmm.
Right?
So that's basically what you're doing, is that right?
Yes, yes.
Okay.
So one question I have is, so you have this very high security in the sense of n-1. I mean, you just need one honest person. But what about denial of service? It's very easy to ruin your computation.
Right.
So what about that aspect?
You're right. I mean, that was part of the discussion at the beginning with Ethereum, that the protocol will be susceptible to this attack. I mean, you're right. It's not protected against denial of service, basically.
Have you done runs with actual people? I mean, actual volunteers? Or...
So there have been several demos. I mean, not in that scale. I mean, with much less. I mean, the scale was, let's say, up to 100. They were distributed. I mean, geographically in different places and so on. But so the answer is yes, but more to come.
Yeah. Other questions? Okay, we are still well past the time. So for me, thank you very much. It was great. Thank you very much to everyone. Daniel, you want to say anything?
Yeah, I want to thank Hugo and Carmit both for speaking and for moderating. G1 as well for the great presentation, and everybody for participating. We hope that you enjoyed today's networking session. It was the first time we sort of sent you away to a different room, and that was because we wanted you to choose where you wanted to go. I understand some of the rooms were a bit small, so we'll have to calibrate that again. Next Thursday, we will have the lightning talks. So make sure to send that your title if you want to give a short talk. And I think next Monday, what we're going to have as a networking session is actually sort of a discussion on what are the next steps in terms of standardization process, sort of a meta discussion on what are those working groups going to be doing by default, and what should be expected from those. Yeah, so again, thank you everyone. If you want to stay and hang out as always, I'm gonna now stop the recording. Thank you again to all the speakers and moderators and contributors and note takers.
And thank you, Daniel.
Thank you.